Most of you have seen polar coordinates before, and so this will be basically a review. But we have this reparameterization that goes from the region 0, comma infinity, cross with 0, comma 2 pi into R2, and it maps the point r comma theta into r cosine theta, r sine theta. And that's what the polar reparameterization does for a living. So in particular, in the xy plane, we'll have that a point r comma theta will map to this point r cosine theta, r sine theta, where this is going to be the angle that so if we draw the triangle created by the point intersected with the point, the origin and the x-axis, if we draw that triangle, then the angle theta is going to be here, and the length r is going to be here. And that's basically the role of the coordinate system. So in particular, we've got this region in the r theta plane. So let's say this is r and theta. And of course we go up to 2 pi in the theta, and we don't include it because we've already counted for theta is equal to 0. And it goes on forever. This region goes on forever. So it's this entire region here. And our map, g of r theta, will take us into the xy plane. Now if we fix a particular r, say 1, what happens to this line under that map? So this line in r theta space, well, it's going to have the same r, so it's the same distance from the origin, and the only thing that changes is the angle, and so that would be just the unit circle, drawn very badly. If we picked another r, we would get another circle of a different radius, so on and so forth. But what about if we took a line where theta is fixed but r is changing? Well, that would give us a ray emanating from 0. So this is actually not there. So that would be the angle pi over 2. So there are 4 of those. So this would be pi over 2. And this would be something more like this. And that's essentially what this map g of r theta is doing. So really the utility that we have here is this reparameterization allows us to do derivatives and integrals more readily. And so it's very helpful to just compute exactly what that warping factor is. So the Jacobian warping factor from g of r comma theta is, well, it's the determinant, the absolute value of the determinant of g1, g2 over dr theta, which is equal to, well, g1 is r cosine theta, so when we take a derivative with respect to r, we just get cosine theta back. Now if we take the derivative with respect to theta, we get negative r sine theta. G2 is r sine theta, so we just get a sine theta here. And then we have another r cosine theta. And what do we get in the long run from this? Well, we get r cosine squared theta plus r sine squared theta, which will be positive. And of course, cosine squared theta plus sine squared theta is 1, so we just get an r here. That's it. And so when we do this change of variables, our factor, or our differential factor, is going to be r dr d theta. And that's probably the easiest thing to remember, r dr d theta. And you can say it like a pirate. That should help you remember it pretty well. R dr, and of course d theta. Next we'll do some examples where we actually integrate